University of Pittsburgh Center for the Philosophy of Science. And Chris Smeenk is Associate Professor of Philosophy at Western University in London, Ontario, and the Director of the Rotman Institute of Philosophy there. I'm very happy to have him. He will be presenting today the work he did together with Adam Kobyrinski named Decoupling from the Initial State. And just before you start, Chris, may I very briefly tell people that we're not planning to take clarificatory questions because this is a webinar and we would have to promote you to panelists in order to ask questions and then demote you again. This is a little bit too cumbersome. So please keep your questions for the Q&A period. With that, I'm pleased to leave you the floor. Please, Chris, go ahead.
Well, let me start by thanking Nick and Chris for the invitation to join the webinar. It's really terrific to be here. I would have enjoyed also visiting Pittsburgh. It would have been great to have a chance to come back, but this is the next best thing. So, and as Chris indicated, I'm looking forward to the discussion, but given the format, I'm not going to be trying to monitor the Q&A during the talk. I just don't feel comfortable handling that. So please keep your questions, and I look forward to the discussion after the talk. And I should also mention that this is based on work in progress with Adam Kobyrinski, and I've also benefited a lot from discussions with Robert Brandenberger, but neither of them should be held responsible for any errors in what I'm about to say. So, right now okay, so there's two aspects of early universe cosmology that the earlier talks have largely, in this series, have focused more on the first aspect of early universe cosmology, a theory of origins or of the initial state. And clearly we need a theory of quantum gravity to deal with this domain, to understand how to resolve the initial singularity, and to sort out the puzzles about the emergence of classical space-time from a quantum gravity epoch. I'm going to be shifting to a later phase in the history of the universe, which is commonly assumed to be described by inflationary cosmology. So according to inflation, there was in the very early universe a transient phase of exponential expansion. So the scale factor grew exponentially rather than the more sedate pace that it would grow in a normal standard Big Bang model. And that this pace, exponential expansion was driven by a scalar field often called the inflaton, and that this is described using semi-classical gravity or quantum field theory on curved space-time. So the question I want to pose today, though, is to what extent does inflation decouple from assumptions about origins? So to what extent can we actually neglect the first aspect of the early universe if we're actually able to describe things using inflation? And so one picture that, so on the left is a fairly standard picture of the history of the universe. This is from the Stephen Hawking Center for Theoretical Cosmology in Cambridge, where we have the time scale going back with the quantum gravity epoch, followed by inflation, followed by different phase transitions. So one idea that has been popular as a sort of methodological approach to the early universe is the possibility that inflation would actually wash away the imprint of earlier stages. So that in effect, if a stage of inflation occurred, we could ignore the earliest phase of this history. So this is an idea about how we could deal with cosmological questions or theories of origins. It goes back at least to the 17th century, perhaps earlier, that we should prefer a theory that's indifferent to the earlier stages. In some sense, it's, if this held true, it would be like an equilibrium explanation, where once a system has reached equilibrium, we can neglect to some extent the path to equilibrium, and we actually lose information about the earlier state. So one question that has been raised since the start of inflation is, to what extent does this hold true for inflation? Now, I realize that for some, this is a depressing prospect, because what it would wash away are traces of quantum gravity effects in the early universe. For others, it's a promising idea that you wouldn't have to resolve all the troubling questions of quantum gravity to have a viable theory of cosmology. And just to give you a sense of the current state of the field, or at least my partial perspective, inflation has been around for 40 years now. It was first proposed in the 1980s. And it's had a striking amount of observational success. So if you talk to cosmologists who look at the cosmic microwave background radiation and other kinds of signals from the early universe, first of all, their observations have revealed that the early universe is strikingly simple, and it can be described fairly readily. It seems that they've been able to rule out competing ideas. So the observations they've made have been able to actually tell us a lot about the early universe in the sense of ruling out competing ideas. And throughout this 40-year process, inflation has still remained compatible with all the observations we currently have. So on this side, inflation has been a striking success. But on the other side, on the other hand, one thing that's striking, listening to, say, conferences on early universe cosmology or reviewing the literature, is that alongside this success, there's also a host of foundational questions that are still more or less open. Now, this isn't unheard of. There's a lot of areas of science where progress can be made without settling foundational questions. But what's striking about the case of inflation, at least to my mind, is that some of these foundational questions seem really quite central to understanding inflation and how it relates to observations. So one of them is just, what is this inflaton field, or possibly fields, that's driving this phase of exponential expansion? A second, which I'm not going to focus on today, but which is a focus of a lot of debate recently, is whether inflation is generically eternal. So does it lead to a multiverse type structure? And if so, what would be the appropriate measure to use in making predictions in that kind of case? And a different kind of foundational question that I think is really intriguing for foundations of physics is, how do the fluctuations of the inflaton field transition from vacuum fluctuations in a quantum field to classical density perturbations? So there's a host of foundational questions that I think the community still has some level of disagreement about, even as inflation has made this enormous progress observationally. So I'm going to adopt a kind of historical perspective on thinking about the nature of this observational success, and one that is really motivated by looking at other cases in history of physics. And this is based on the idea that I think in physics, we require and expect more of our theories than fitting the data. And so the theories that we have a great deal of confidence in do more than just fit the body of data. They give us an understanding of the idealizations and assumptions used in constructing the models that we use that fit the data, such that discrepancies with observations can be used to discover further details about the phenomena. And so that the theories, because they have this because we have this level of control over them, can form the basis for ongoing inquiry, that we can use the theories to discover more about the domain of phenomena that we are interested in. And I think it's theories that have this structure that can successfully respond to the threat of underdetermination. So I think you can argue, if you have a theory that allows you to make discoveries in this sense and supports ongoing inquiry in this sense, you can then reply to worries that there might be another theory equally compatible with the data. Now, this is partly based on work by George Smith that I'm drawing on here. I'm not going to defend this in detail, but I just want to indicate that my perspective in asking, what does the observational success of inflation warrant, or how should we think about that? This is the kind of framework in which I formulate that question. And then coming to inflation, I think the obstacles to seeing inflation as founding ongoing inquiry in this sense are related to exactly the question that I raised before, whether it's indifferent to the earlier state. So the obstacles to seeing inflation as supporting ongoing inquiry in the sense that I've described are that it does seem sensitive to UV physics, And there are specific ways in which it doesn't decouple from the physics of the earlier universe. And finally, inflation, despite its ongoing success in matching observations, still has an unclear connection to fundamental physics. So that's really the set of issues I'm going to focus on in today's talk. So before going into that, let me very briefly introduce the ideas of inflation and say something about the basic structure of the theory. So, and I'm not going to go into a lot of detail here, but just enough to frame the later discussion. So we can think of inflation as starting off with a hypothesis that in the early universe, there was a scalar field or fields that has a particular kind of effective potential. And furthermore, that there exist regions, space-time regions, where that field is in a uniform state so that we can neglect, gradient terms that would appear in the stress energy tensor. So the stress energy tensor for a scalar field will have other terms, but if the scalar field is uniform in a region, those derivative terms are negligible. And so if the scalar field satisfies those kinds of constraints, then its effective stress energy tensor will just look like the, and if it's displaced from the true vacua, then it will just be the vacuum energy associated with the false vacuum times the metric. And that's an effective cosmological constant term. And so if these conditions are satisfied, and this is something we'll come back to later in the talk, the idea is that this field in its false vacuum state would then dominate the expansion, and this leads to a quasi-de Sitter phase. So it dominates the expansion just because if it's an effective cosmological constant term, it doesn't dilute with expansion like other forms of matter and energy would, and so it would come to dominate the matter and energy content of that region that is now inflating. And the idea is that, eventually the other forms of matter and energy will dilute away, and then you approach the solution, which would correspond to just a cosmological constant term, which is a de Sitter space. So there are results. So the reason I have a question mark there for the consequences is that, as we'll see, there are results which fill in specific details of this hypothesis in order to assess what are the constraints required for this kind of domination of the dynamics to occur. So this is something that you have to be more precise in the statements in order to have a clear theorem, but this is the physical intuition behind how inflation would come to dominate if the scalar field has the appropriate properties in some region. And sometimes more loosely, inflation is just defined as an inflationary phase where the scale factor is just has the second derivative of the scale factor is positive. So that's again a phase of accelerating expansion. So this is a looser definition because it doesn't require that you exactly approach a quasi-de Sitter solution as I've described it, but just a phase of accelerated expansion. And so so that's then the hypothesis that you would have a phase of accelerated expansion in the early universe, typically assumed to be driven by a scalar field in a false vacuum state. But again, this is a much more general idea. So you could have other physical sources driving that phase of expansion. And the most important consequence of that phase of expansion, this was recognized by Mukhanov before the development of what we think of as the inflationary model due to Guth, is that this gives rise to an account of how initial fluctuations in the vacuum field will physically evolve through this expansionary phase. And I'm going to do this this will be a hand-waving discussion, but this is the essential picture that has emerged of what happens during this inflationary phase. And the important point is that if you imagine a fluctuation mode of the initial scalar field, there's a contrast between how the Hubble radius evolves during an inflationary phase and how that mode grows during the inflationary phase. And this is illustrated in the diagrams on the left. So during an inflationary phase, the Hubble length or the Hubble radius is almost constant. So there'll be a slight slope, but it's almost constant during this phase. And what you have, by contrast, for the evolution of one of the modes of the scalar field is that it will be growing during inflation. And then the growth of the mode will slow after inflation ends, whereas the Hubble length will go from being a constant to then growing. And so what you have is 2 points, which are indicated by the dots in the diagram. The first is where a mode exits, goes through the Hubble radius and becomes super Hubble, and then it re-enters and it becomes sub-Hubble. And the equations that they're called the Mukhanov-Sasaki equation, describe the evolution of these modes. And those two regimes correspond to different types of behavior. So we have adiabatic evolution for the modes that are below the Hubble radius, sub-Hubble modes, and they're overdamped for super Hubble modes. And so the horizon exit reentry then leads to these modes freezing out as they exit the horizon and then coming back in as the source of classical density perturbations. And this physical picture of the evolution of the modes of the inflaton field during an inflationary phase then leads to a specific set of predictions that depend on the details of the effective potential, which will determine exactly how this inflationary phase transpires. But it leads to predictions for the characteristics of those density perturbations in the post-inflationary state. Their spectrum, the ratio of the scalar to tensor perturbations, there's different types of perturbations that can be produced, and their amplitude, and so on. And so this physical idea is really the workhorse of inflation. So when I described earlier that inflation has been compatible with observations of the CMB, really this aspect of inflation is what is being probed by those tests, because the tests are really about the output of inflation in terms of its picture of density perturbations. And again, this is something that deserves a lot more time to go through with care, but just very briefly, this is data from the Planck collaboration. So given that account of the formation of density perturbations through the inflationary phase, we first of all see that the general picture we get from inflation is compatible with what we in fact see in the angular power spectrum, which are the data represented on the top left. And then we can also ask for particular model types of inflation, what kind of constraints we can put based on those observations. And so in the bottom right, the two properties that are that characterize this parameter space are the primordial tilt that characterizes the so a tilt of 1 corresponds to an exactly scale invariant spectrum, and inflation predicts slightly less than 1 tilt, and that reflects the fact that the Hubble radius isn't exactly constant throughout the entire inflationary phase. And so that's one of these axes. The other axis is the tensor to scalar ratio that characterizes the amplitude of the scalar perturbations compared to gravitational wave perturbations. And so the CMB results are able to constrain these and other parameters of the inflationary models. And you can see from the way that Planck, the analysis is quite complicated because it's model dependent. So they have different classes of models that leads to all these different overlapping colors. But just as an illustration, we can see that in this region, this is called R-squared inflation. This is one of the original models of inflation proposed, or perhaps the original model of inflation proposed by Alexei Starobinsky, fits well within the confidence contours for the combined values of NS and R. So this then is the observational program related to inflation is really getting tighter parameter constraints on the space of models, given observations of the CMB and other phenomena in the early universe. And this has led to an approach. So for example, Jerome Martin and his collaborators published a review paper a while back called the Encyclopedia Inflationaris, and they consider almost 200 individual models. So it's a real, there's a lot of models that have been proposed for inflation. They fall into sort of 74 different types. And what they're able to ask then, they use a Bayesian inference model to ask which of these models is preferred. And it turns out that the plateau models, those originally described by Starobinsky in 1980, are models like that are the preferred ones. But in essence, what this project is doing, so for a simple scalar field model, they're using the observations of the CMB to constrain the things appearing in a Lagrangian. So this is if we had a single scalar field model. There's something called the effective potential here, and then also an interaction term, which characterizes how the inflaton field couples to other fields that appear in the standard model. And what these constraints are effectively constraints on the features of the effective potential and of the interaction term. So the project is to use observational results to determine the parameters appearing, or the functions actually appearing in the Lagrangian. So as I said, inflation has been successful in the sense that there's a large variety of inflationary models that fit with all of the available data. And there've been, and there's some selection, there's some models now that we can say fit better or worse with the Planck data. Now, alongside this development in considering the observational impact or the observational consequences of inflation, there's also been really persistent debates about the foundational questions related to inflation. So for example, so this is from a Scientific American article by Paul Steinhardt. Steinhardt, EOS, and Turok have also published papers after the first round of Planck results. One of the questions that they ask is, how plausible are the models favored by observations? So we have a framework that allows us to choose the best fit models that are favored by the data, but they push a different kind of question. How can we assess whether those are physically plausible? Do they give us a physically plausible description of the early universe? And they raise a question that has been raised throughout the history of inflation. How likely is the initial state that's required to create an inflationary phase? So I stated it as just a hypothesis. Imagine that you have a field with the appropriate properties, and there's a space-time region in which it has the appropriate properties to start an inflationary phase. How likely is that? How do we assess probabilities in that kind of case? And also, I think behind some of these criticisms is a worry that the success in fitting the data really just reflects the flexibility of the inflationary paradigm. We have a very large space of theories. We have functions that we can fit to the data. And so how is it that we should have confidence in the framework as getting the appropriate physics as opposed to just allowing us to fit the data because of its flexibility? Now, these are all, as I said, I think they're all still active debates. There's a sociological question about how many people would raise these questions as serious challenges. I think it's clear that inflation is the dominant paradigm in early universe cosmology. So I don't want to misrepresent the situation in saying that these debates have, they're not a majority view, but this is something that I think there are questions that have been raised throughout the history of inflation that even despite the success in the observational program are still being raised. And I don't think also that there's a sort of consistent conventional wisdom among the community about how to respond to each of these foundational questions. But what I want to focus on now in the remainder of the talk is a particular aspect of these debates, which is to ask, can we treat inflation as an effective field theory? And what are the limitations of doing so? So the kinds of calculations that I described in a very hand-wavy fashion earlier, such as that regarding the evolution of perturbations, are ultimately based on using quantum field theory in a curved spacetime. So we usually think of fields evolving over a fixed classical background, or in some cases, we're able to do a semi-classical calculation where we include back reaction effects. And we typically assume that the state of the inflaton field is in a Bunch-Davies vacuum state in these calculations. So the questions regarding these calculations really focus on how reliable they are and how sensitive are they to quantum gravity effects. So can we actually have confidence that we understand and have controlled the idealizations involved in these calculations, because we're neglecting some aspects of classical gravity and also quantum gravity? And here, I think the hope is that we'd have something like the decoupling that we see in other effective field theories. So again, just as a very brief sketch, in the effective field theory program, we often want to consider, or using effective field theory techniques, we often consider some set of correlation functions among operators for a field theory with an action S. But if we now restrict to a set of operators, which we think of as low energy operators that are only apply at some much lower energy scale, what effective field theory techniques allow us to do is construct an effective action such that we can do calculations for these correlation functions using this effective action. And in several cases, we can prove that these will agree with the original correlation functions for the full theory up to some specified level of precision. And so we can have a very precise sense of decoupling in cases where we have this level of control. So there's often a contrast between top-down construction of effective field theories versus bottom-up. So if we're able to build a top-down effective field theory, we can explicitly integrate out the high energy degrees of freedom from an existing theory in order to obtain the effective action. And then we can prove whether that effective action will actually decouple. And in some cases where we don't have the high energy theory, we can still argue that by including all the terms compatible with symmetries in the effective action, if we make sort of weak assumptions about the higher energy theory, we can claim to have constructed an effective field theory that will decouple in hopefully much the same way as the top-down construction does. And so what I mean by decoupling is that there's a very nice separation of physics at different scales. And the way this is reflected in these calculations is that the high energy physics has limited impact on the low energy EFT. And if effectively, well, it really just shows up in the values of the coupling constants in the low energy EFT. So in cases where this works, we have a very nice picture where we don't have to worry about the details of the high energy physics in using our low energy EFT, because we have a clear understanding of where the high energy physics would have an impact and the limitations of that impact. So this is a well understood idealization or approximation, and we would have control over the degree of what we're missing in effect by working with the low energy theory. So the question then with regard to inflationary theory is, are there senses of decoupling that also hold for inflation? So can we argue that inflation decouples from details of quantum gravity? And I'm going to argue that inflation, unfortunately, seems to be very sensitive to UV physics. Again, it's a matter of perspective. If you're interested in quantum gravity, then it might be, fortunately, that it's sensitive to aspects of UV physics. So let me focus on two different senses, and I'm using decoupling in a slightly looser sense in this slide than in the previous slide. So the first question is, when we're describing inflationary dynamics as a scalar field on a classical background, can we say that that is an EFT that decouples from UV effects in quantum gravity in the sense that I used it on the previous slide? And then there's the second question regarding decoupling, this is the case that's a bit looser, which is really a question of how indifferent is inflation and the outputs of inflation to the details of the pre-inflationary state. So how robust is the output? So we have a post-inflationary state that includes a set of density perturbations with certain properties. How robust is that post-inflationary state to variations in what the situation is like before inflation? So, and there's two aspects of this question. Is an inflationary phase a dynamical attractor? And are the predictions robust to variations in the initial state of the field? So do we have to assume that it's in a particular vacuum state in order for the predictions to follow? So let me take the second issue first. And this is a question that's been, that was posed in a classic paper by Goldworth and Perron, and there's been a series of different ways of tackling this question that differ in the sort of sophistication that they're able to use, and a lot of them involve numerical relativity methods, and also then in variations in exactly how they, the assumptions that they're able to make about these two questions. So the assumptions that have to be stated clearly in order to prove a theorem of this sort is, what are the restrictions on the space-time geometry of the patch that you're starting with? And what are the properties of the inflaton field in that patch? And so what we want is a proof that given assumptions of that sort, that locally will have an attractor behavior, namely that variations away from a certain simplifying set of assumptions will be stable. They'll also lead to a trajectory that undergoes a long period of inflationary expansion. In other words, that an effective lambda term dominates. And so some of the early results, for example, you had to assume that you were effectively in an FLRW geometry or very close to it. And similarly, for the properties of the inflaton field, you might be able to construct a case where you have some inhomogeneities, some gradient terms, but you have to put a limit on those. So there are a lot of results. I think we still don't have, my impression is that we still don't have a completely general theorem of this kind showing that inflation is an attractor over all the range of cases we'd be interested in. And secondly, the verdicts vary for different types of models. And so this ends up being a very model dependent question where, depending on the shape of the effective potential and how much, so what are called large field versus small field models, that characterizes how much the sort of variation in energy scale of the field over the course of inflation. Given these different types of models, some of them have more severe initial conditions problems than others. So there's some evidence in particular that large field models do seem to have a local attractor behavior, but small field models have a more severe initial conditions problem. And this I'm drawing from a relatively recent review of this literature by Robert Brandenberger. So there's been a lot of progress on this. There's some understanding then of the cases in which inflation acts like an attractor dynamically, but there's still not a completely general result. And in some cases, it looks like models actually aren't, or it looks like they do have a severe initial conditions problem. So that raises a worry for those models of whether we should, this goes back to the worry about the probability of the initial state. If they don't exhibit an attractor behavior, then it looks like we would have to have a special pre-inflationary state in order for inflation to arise. Okay, so there's a further question then about the nature of the state of the inflaton field itself. And it is the case that the structure formation predictions assume or require that the state of the inflaton field is a Bunch-Davies vacuum, which is a vacuum state that's in some sense a locally Minkowskian vacuum state. And there are results showing that other states for the inflaton field will lead to non-scale invariant spectra. So then an important question: why should we expect the fluctuation modes to be in a Minkowski vacuum state? In this very general setting, we're imagining the pre-inflationary state is a bloom and buzz and confusion, a lot of fields in very high energy excited modes. Why is it that we find this field in a vacuum state, and also one that's in effect a Minkowski vacuum state, even though we haven't put in any of that space-time geometry by hand? And this problem is exacerbated when we think about what the wavelength of the modes are that are going to actually be relevant for the observations in the CMB. So this depends on exactly how long the inflationary period lasts, but if we extrapolate back a length scale that's roughly the Hubble radius now, and we extrapolate backwards to just using the standard FLRW model, so there's no inflationary phase, what we get back to at a high energy scale would be something on the order of centimeters, right? So that's the length scale associated with the Hubble radius, just under standard FLRW expansion. But if there was an earlier inflationary phase, that scale would be much, much below the Planck length, which then expands during inflation and then continues on to expand and becomes a mode with the wavelength of the Hubble radius. And so this means that our assumptions about the pre-inflationary state are not just assumptions about super Planckian wavelength modes, they're actually deep in the Planckian regime. And so again, if we make the kind of standard assumption that below the Planck length, we have to take quantum gravity effects into account more seriously, we're obviously not doing that if we're just assuming that the inflaton field is in the Bunch-Davies vacuum state for all of those modes, including the ones that are sub-Planckian. So this is then called the Trans-Planckian problem. This is something that Jerome Martin and Robert Brandenberger raised in 2001. There's been a lot of discussions of it. And as Francesca mentioned in a previous talk in their series, there's been loop quantum gravity calculations regarding the status of the Bunch-Davies vacuum state as well. So people have looked at giving a quantum gravity treatment to try to understand what the status of that assumption is. And so partly motivated, I think, by this problem, and in relation to string theory, Bedroya et al., and including a paper in collaboration with Brandenberger, have recently advocated what they call the trans-Planckian censorship conjecture. And the way I understand this is that the conjecture is that we would rule out the possibility that I just raised as a worrisome one. Namely, we would rule out the possibility that fluctuation modes with a trans-Planckian wavelength would ever classicalize by exceeding the Hubble radius. So what that would introduce is a constraint on the evolution of the scale factor. And this is the equation here gives a constraint that if we imagine considering some initial time where we've set the vacuum state and consider the wavelength modes at that time, then we'd say they'll never expand so that they go beyond the Hubble radius and freeze out as classical density perturbations. So this is an interesting kind of epistemically motivated conjecture. It's really saying to preserve our ability to do calculations, we'll assume that the quantum gravity effects will never show up. And so we'll require that our cosmology doesn't stretch these sub-Planckian modes to be something that would be observable. And if we accept this conjecture, this implies constraints on the energy scale and the shape of potential for inflation, because most models of inflation will lead to stretching of the sub-Planckian modes to over the Hubble radius. Now, part of the motivation for this is related to something that's in a sense above my pay grade. This is the swampland conjectures from string theory. This is a set of conjectures that low energy EFTs of various sorts are not actually compatible with string theory. And so there's a related set of constraints that people have worried about for several years now regarding whether you can have a de Sitter solution within string theory. And if that's not possible, or if there are constraints from string theory on what the low energy EFTs can look like, then that also imposes constraints on inflationary models. And so in the original discussion of this, the part of the motivation for the censorship conjecture was from string theory and from these swampland conjectures. So this has produced a lot of discussion and controversy since it was, even though it was proposed very recently. My interest is not so much to take a position on this particular issue as to illustrate how a conjecture about string theory could constrain what we want to say about the effective field theory treatments of inflation. So if this were true, then we would have an unexpected constraint on the kinds of models that we can consistently build for inflation. Now, obviously, this can go both ways. One way of responding to this is to say, so much the worse for string theory. If it isn't compatible with inflation, then we should, in fact, revise the swampland conjectures. But the point is, it's a constraint on the lower energy EFT that is unexpected if you thought that the inflationary EFTs decoupled in the way that you would like from the UV theory. Okay, so this is part of a more general set of questions about how to apply effective field theory techniques to cosmology. So these techniques have been applied successfully to gravity. So Cliff Burgess has a number of nice review articles on how EFT techniques have been applied to gravity, as well as Donahue. And they overall are applied in regimes with symmetries. If you have, for example, static or slowly evolving models, or if you have asymptotically flat models. So they generalize, so EFT techniques, at least as commonly used in particle physics, often use the structure given to you by Minkowski space. You can generalize away from that and use and apply EFT techniques more broadly. Essentially, you need to make sure you have a way of defining a separation of energy scales and some other features in order to assess the decoupling between different separated scales. But in general, I think it's less clear that we actually have a good handle on applying EFT techniques, in particular in expanding models and models that lack the symmetries that we have that have been employed in existing constructions. So I think this is the problems with using EFTs in inflation are related to this broader problem of how to use EFT techniques in cosmology. And let me just indicate one thing that I take as a reason for worry about applying EFT techniques in cosmology. I'm just going to mention this and not go into detail, but Frank Wilczek in 1983, in one of the very first workshops on early universe cosmology, where a lot of the ideas about inflation were actually developed. Oh, sorry, I don't know if you can see that, but I just gotta, I'm not sure if you're seeing my screen, but okay, sorry, I just had a software interrupted me briefly. So Wilczek said in this conference, it is surely an act of cosmic chutzpah to use this dismal theoretical failure in understanding vacuum energy and the cosmological constant as a base for erecting theoretical superstructures. But of course, this is exactly what is done in current inflationary models. And that is exactly what is still done in current inflationary models. And despite a lot of work in the last 40 years, I think it's still safe to say that the cosmological constant problem is not one that we have a clear understanding of. This is something that's drawn the attention of some philosophers recently, trying to understand the nature of the problem. Again, I take it as an indication that we have some difficulties in applying effective field theory techniques in gravity in cases where things like the cosmological constant are relevant to the evolution of the space-time, and clearly inflation is one of those contexts. Okay, so I realize this was fairly brief, but let me wrap up just by highlighting a few of the points that I've tried to argue for, and then I'm looking forward to the discussion. So first, in terms of the question I started with, is it possible to think of inflation as giving us an account of the universe that's entirely indifferent to the initial state? Again, I think for some theorists, this is seen as a good thing, that you could resolve the problems of cosmology without actually having to solve all of the mysteries of quantum gravity. But I think it's clear that we can't forget about the early state, at least given what we currently understand about inflation. Inflation is sensitive in various ways to assumptions about the earlier state, and we don't seem to have a full understanding of the dynamics and how it relates to fundamental physics. And I think that in some ways, this is actually an appealing prospect. We can see the possibility for further insights into quantum gravity based on how quantum gravity relates to inflation. And in some sense, this isn't a surprising conclusion. We can think of inflation as, rather than being the full story of the early universe, it then ends up looking more like Big Bang nucleosynthesis, an interesting dynamical part of the evolution of the universe, which does require some earlier assumptions. And if it's true, then has dynamical implications that we can check through observations. So rather than being something that washes away completely the earlier state, it's just another phase of the dynamical evolution of the universe, which we can then try our best to evaluate. And the second point is that I think inflation is something that's been fascinating to me for many years now, partly because there are these interesting, persistent foundational debates. And what I've focused on here is the challenges in connecting inflation with fundamental physics and clarifying the domains of applicability of EFTs, and in particular, how we can use EFT techniques in thinking about gravity. And so I think this is not something I've pursued in this talk, but I also think that understanding how inflation deals with these foundational challenges also needed to assess inflation by contrast with a variety of other early universe scenarios. So one thing that's happened within the last, within the last 20 years, there are now a variety of other scenarios of what could have transpired in the early universe that connect with theories of quantum gravity in very different ways than inflation. And although they certainly have not captured as much interest and attention as inflation, I think in order to make the case that inflation is better or worse than them, I think these issues really need to be sorted out. So with that, I will conclude and look forward to your discussion and comments. So thank you.
Excellent. Thank you very much. Okay. I see we have already 3 people who have raised their hands. And as Nick and Shaheen has said in the chat previously, the way we're going to do this is a little bit different from the way we did it so far. So please don't write your name in the Q&A section, but instead use the raise hand function. When you do that, it'll show the order of the people who have raised their hands, and I will take them in order, promote them to panelists, and when I do that, don't be worried, because it looks to you as if you're disconnected for a moment, but you should be immediately reconnected and then be able to ask your question. Okay, so let's get started. David Wallace is the first one. As soon as he is back with us, please. David, it's your turn.
Thank you. Thanks, Chris. There's like about 40 questions I could ask, so I was trying myself to one for the moment. I wanted to ask a bit more about how you're conceptualizing the this transplanckian issue of the short distance modes. And I'm particularly interested in terms of the parallel with how that's treated in Hawking radiation considerations. So in black hole evaporation, you've got something similar. The dynamical origin of radiation is that I'm redshifting, I'm exponentially redshifting modes very close to the black hole horizon.
Mm-hmm.
And then that's turning up as thermal radiation. Again, there's a concern that if you take the calculations completely literally, then in logarithmically in time, then the low energy radiation depends on Transplanckian modes.
Mm-hmm.
Now, in that case, I mean, two things that seem to come out of the literature on this is, one of them is you don't want to be taking the theory literally at the sub-Planckian scale, just it's an effective field theory. That's not a domain where field theory is trustworthy.
Yeah.
What you've got more is this is an aspect of an effective field theory we don't normally see in the Minkowskian domain, because we basically have to keep repopulating the bluest modes in the vicinity of the horizon, and we need a rule for how to do that.
Yeah.
That makes the evolution non-unitary in certain senses, interesting in certain senses, and in a certain sense, any hypothesis about how that works is then a hypothesis about quantum gravity.
Mm-hmm.
So I suppose the comment is, I wonder if think of it in terms of we need to make substantive assumptions about the state is maybe not quite the right way to put it. We're making substantive assumptions about the way in which we couple to unknown physics in some sort of more generalized way.
Yeah, that seems exactly right. So the probably a better way of putting the question is, what do you think is the state of the modes as they cross the Planck length? So as you say, how do you characterize the modes as they cross some limit of domain of applicability of your effective field theory? And as you say, the same kind of questions arise. You have, in some sense, a failure of unitarity because you have new modes coming in. And there's actually a parallel between some of the responses to the Transplanckian problem in the case of cosmology, in the case of black hole physics, which is that Unruh and others looked at modified dispersion relations as a way of trying to assess, give us a very specific change to the state, see what the impact is, are the results robust under that? And so there's similar arguments in the inflationary literature. So I think there's actually a very close parallel. But I think the part of the question is, in the case, I don't know how to assess this in the black hole case because I just haven't thought about it as much. How then do you assess the plausibility of those assumptions about the coupling of the modes or the quantum gravity effects that might be relevant for those modes as they cross the Planck length? And I think that's there's been more of a debate about that in the cosmology case, or more disagreement about what's reasonable.
So I mean, the question I wanted to ask was, I mean, in the black hole case, one of the I think strongest, but also most commonly seen arguments you see as to why the conjectures, the necessary Hawking supporting conjectures appropriate there, is that it's a condition for the local validity of the equivalence principle. In other words, if the freely falling observer crossing the horizon is going to see something that looks locally like the vacuum, then you need something like these sort of assumptions in place. This is the Jacobson runs this kind of argument. So bypass considerations of what was going on in the indefinite Transplanckian past. Ask yourself what in the present would have to be true about how we repopulate modes to preserve the equivalence principle for those observers. And then you can think about that as I mean, in the spirit of what you're saying, as an infrared constraint on what the ultraviolet physics looks like, but a direct one. And I'm wondering if there's any, I can't think how it would be done, but I'm much less familiar with the physics here. Is there an analogous kind of equivalence principle validity constraint that we can think about here?
That's interesting. I haven't thought of that, and I'll have to think about it a little bit before getting back to you. I mean, I think the shift in perspective is certainly interesting, but I don't know, there's no immediate analog of the infalling observer that comes to mind that.
Yeah, I mean, the nearest I can think of is going to be something like, the black hole exterior space-time has quite a lot in common with the kind of the de Sitter wedge, where we just have a triangle on the right-hand side of the Sitter space, and the falling observer has quite a lot in common with just the inertial observer at some finite distance from the arbitrary origin who crosses the de Sitter horizon in finite time.
Right.
And then the kind of Transplanckian concerns about Hawking radiation are going to translate over to Transplanckian concerns about Gibbons Hawking. I mean, get the de Sitter version of Hawking radiation. I forget what it's called.
Right.
Now I've exhausted what I could think of on the framework though, because conversely, I don't know the cosmological framework well enough to have a sense of how that maps over to the inflation issues.
No, that's interesting. So I'll have to pursue that and get back to you. I don't have anything I think helpful to say right off the top of my head, but
Thanks for the talk.
thanks.
Thank you very much. Mike Schneider is next. Please, Mike.
Hi, Chris. Thanks for all of this. I think this is a subject that I'm very much interested in.
Mhm.
And I wanted to, I guess, I'll frame this as I wanted to push you into maybe having a controversial thesis that I may happen to agree with or disagree with. And it's about the two senses of decoupling. That's how you phrased it. So it seems to me like, far from just being two different interesting notions of decoupling, they're in fact radically opposed to one another, in that our thinking about one, if we want to formalize the effective field theory adjacent sense of decoupling, the sense of decoupling at work here is opposed to one in which we think of an earlier state decoupling. And that's just because of the use of the word scale, for lack of a better demonstration of the point. So to get it working, you need a notion of scale in space-time, or something that's going to look sufficiently close to that really what we're talking about is a, say, coarse graining at a moment in time type decoupling. Whereas the other sense of decoupling from the initial state, is it's a more rough and ready modelers type of decoupling, where you're just saying that everything past then is outside of some boundary conditions, and so we can ignore it as long as we've got the right information as initial data or something. So do you think that there is this radical tension between these two senses of decoupling, or is there a way of treating them simultaneously and letting them both do work in our thinking about quantum gravity?
Yeah, I mean, I'm not sure that I'm going to fully respond to the question, but I think that maybe a better way of thinking about them is criteria of adequacy for modeling that have slightly different flavors, but that both relate to assumptions about physics in a different regime, right? So it's sort of the reason I was thinking of them both as decoupling in a loose sense is just that they both involve assumptions about how the quantum gravity effects come into play, right? And they both are questions of to what extent can you ignore the sorts of quantum gravity effects. And I don't know that, I mean, and I'm totally happy with saying they have a different character, right? There might be different ways that your models break down. One of them is a kind of sensitive dependence on initial conditions that you don't have sufficient control over, right? So if you fail to have the attractor behavior, then that's the problem that arises. The other is more that the dynamics itself is not well defined, or I think what to me the swampland conjectures and other things raise is the possibility that you've constructed a dynamics that looks fine within one regime, but is actually contravening some fundamental physical principles that hold in the higher energy physics. Another thing that sometimes arises is questions of if you're taking the bottom-up approach to constructing an EFT, what symmetries do you use? And in particular, you might have symmetries in the higher energy theory, such as a UV-IR symmetry, which would radically change how you construct the EFT. So that's again, I don't think it's a dependence on quantum gravity and whether your EFT models are reliable, but it's not the same as the sensitive dependence on initial conditions kind of issue. So again, I'm not sure that I've quite got the thrust of the question, so feel free to redirect if there's.
Yeah, so I guess, what you just said sounds good to me, and to sort of keep a liberal mind of the many ways in which we could get constraints from a quantum gravity regime. I think that's great. I guess the force of my question, or the place that I am getting worried about, is whether I'm allowed to think that simultaneously there could be both of these kinds of constraints, or if a particular quantum gravity approach is going to favor one over the other and vice versa, or so on.
Okay. I mean, they do seem like they're distinct constraints, but there could be an interplay. Yeah, I mean, I don't see anything to rule that out, so.
Yeah, I guess the push would be, or the source of my worry, the locus of my worry, is that it seems like the effective field theory adjacent type of decoupling or sense of decoupling is a straightforward reduction story, and that's certainly how it seems to me it's talked about in the swampland context.
Mm-hmm.
Whereas the more traditional, the dating back to 1700s line of decoupling is, it's not a reduction story. It's a sort of fact of the matter, causation in the, causation in time, sense of cause type of decoupling. And if we're going to help ourselves to the reduction story, then we're moving from models of the, say, semi-classical theory or the quantum field theory and curved spacetime to the quantum gravity models, which are all of spacetime. And so then I would lose the sense in which there is a sort of cause in time structure to give us the worry about the initial conditions.
Interesting. Yeah. So if you're really thinking of an emergent space-time, then some of the ways that we divide up these might not actually hold. Okay. That's probably right. I mean, you're certainly right that the stability considerations are something that go back some time. That's just usually a kind of adequacy criteria for applying mathematical models of a certain sort, right? So you're right that that's a very general consideration. It isn't something that's specific to this context, but as you say, it could break down if we have actually a quantum gravity theory in which there isn't the kind of clear division between space and time that picture kind of assumes. And then, yeah, I don't know what to say about whether those are two aspects of the same concern. Let's.
All right, well, thank you. As I said, I enjoyed this entire talk.
Thanks.
Thank you very much. The next question comes from Arno Keppens, please.
Can you hear me well?
Yes.
Okay, thanks for your talk, Chris. I have a question that is somewhat more on the conceptual framework and that touches on the emergence that was mentioned by Mike. So your discussion on decoupling during or on inflation reminds of thermodynamics theories where you have during a phase transition, for example, a dependence on the constituent properties in the thermodynamical system, or where the phase transition, as inflation could be considered, depends on the state variables, which in this case could be a metric, I don't know. Have you considered, have you deliberately not used this kind of terminology or framework, or have you worked in this direction?
I haven't used that framework for thinking. I mean, in some sense, inflation is usually thought of as a phase transition. So in that sense, it's sort of in the background. It's just not something I emphasized. I'm not clear. So is there a thought that this way of thinking would also help to understand the questions about the reliability of effective field theory techniques by looking at how those are used in modeling phase transitions, or
something like this? Have you considered this line of thought in your work, or this approaches where people look at dependence on constituents within phase transitions, something like this?
Not really in detail. So, I mean, I'd be interested if you have some references to send me about this might be a promising new line to pursue. As I said, in some sense, the early universe theories do just describe a series of phase transitions. So I've thought about it just in those generic terms, but it wouldn't surprise me if there's sort of a richer way of thinking about phase transitions from a condensed matter physics point of view that might be helpful in thinking through these issues.
I think, yeah, typically analog gravity approaches come to mind, have also considered Big Bang scenarios. So something in this direction could or might give indications towards your work as well. I don't have a specific paper in mind, but you could have a look there.
Okay, so I didn't know. So analog gravity people have been trying to simulate aspects of early universe phase transitions. I wasn't aware of that. I knew they were trying to do things like Hawking radiation.
At least, yeah, expanding space and then with backwards extrapolations.
Well, thank you. That's interesting.
Thank you too, Chris. Bye.
Thank you very much. The next question comes from Siddharth Muthu Krishnan, please.
Hi, thanks. So this is not a field that I know much about, so I just wanted to get to understand the lay of the land a little bit more. So just first let me see if I understand the dialectic correctly. So there's the inflationary cosmological model that's meant to explain things like the horizon, the flatness problem, and the homogeneity problem, and all of that. And it works in that way, but then it has this kind of initial condition thing that you need, and your argument is that you can't quite get that initial condition using the kind of standard effective field theory arguments that we use. Is that a fair summary, I think?
Well, that's part of it. I mean, I think the overall question is, to what extent do we understand the limits of applicability of the effective field theory models that we're using in inflation? And so part of that is related to the initial conditions problem. And then part of it's also just related to, is there a clear way of understanding how the inflationary models relate to fundamental physics?
Okay, I see. So that's just two separate questions. One is, how does it even relate to fundamental physics? And the second is, how do you get the initial condition? Okay, great. And I take it, just to make sure I understand the lay of the land, the kind of sort of string theoretic approaches haven't been very successful in telling us how they might possibly relate to fundamental physics.
Well, this is something that I sort of left out at the end when I mentioned that there were alternative scenarios for early universe cosmology. And so there are a number of scenarios that people have pursued that are more motivated by string theory. And it's been, again, this is a very contentious area that some string theorists believe that there's a fundamental problem with having a de Sitter space as a solution within string theory. And so that raises problems with both inflation and accounting for dark energy. Other string theorists don't have that view. And so this is above my pay grade. I'm not going to try to assess those arguments, but there have been other alternatives to inflation that are more directly string theory motivated. And so I mentioned that Steinhardt is one of the people who's been very critical of inflation. He's also advocated an alternative called the ekpyrotic universe. And then there are some other alternatives. Robert Brandenburger has some really nice reviews where he has discussions of string gas cosmology and other alternatives that have been developed. So there are very different accounts of the early universe. One thing that is striking to me about them is that, and this is related to, for example, if you think of this in terms of Ricard David's no alternatives argument, one way of thinking about what an early universe theory should do is that it should tie together a bunch of properties like flatness, the horizon problem, and the density perturbations. And one of the things that's striking about these alternative theories is that most of them focus completely on getting the density perturbations, because that's the thing that has been the most fruitful contact with observations. And so they don't look like alternatives to inflation in the sense that they don't do exactly the same things as inflation. What they do is they redefine what an empirically successful account of the early universe should do. And it's really just, they should have an account of the CMB observations. And that's the focus.
Okay, great. Yeah, I think you addressed part of the question that I was going to ask at the end, which was, yeah, I had heard about these Steinhardt-Kurok style models, and I had heard that they don't sort of have, at least according to some of their partisans, that they don't have this kind of initial condition problem that inflation has. So I was curious whether, yeah, that solves these conceptual problems more, but if I understand you correctly, it's still not even clear whether it's empirically successful, right?
Yeah, so the initial, the sort of likelihood or probability problems that are raised by Turok and Steinhardt and others, those are really tricky because there's kind of two different aspects of the probability questions. One is they take, and again, this is a somewhat contentious issue. I think probably the majority of people working in inflation with would agree with this. So Guth and a number of other people say that inflation is generically eternal, and then that leads to a multiverse structure. And then there's a question about how to talk about probabilities in that structure. So there's a different question, which is, what is the probability that there was a region that had the right properties to inflate? And there's a different way of trying to assess that question. And one of the arguments that given, so they criticize the multiverse picture, but they also argue that inflation is unlikely given that assessment of the probability assigned to different pre-inflationary states. And then they also argue that the particular models that seem to be favored by the Planck data are the ones that have this sort of initial conditions problem is the worst for those.
Okay, thank you.
Thank you very much. The next question is from Nick. Please go ahead.
Hey, Chris. Thanks for a great talk that really laid things out very nicely. I really kind of appreciate it. Maybe in part of advertising the project, I'll mention that Robert Brandenberger gave us a talk earlier in the year on sort of his views on some of these similar matters and fleshing out some of the things that you were talking about. So people can find that on the project website. And I put a link to that so people can access all the talks in this seminar series as well into the chat. So at the beginning, so here's my question. At the beginning of the talk, or early point of the talk, you mentioned the sort of empirical successes of inflation, and I think you said, what I hope to do is tell you how to think about, sort of evaluate those empirical successes. And I think I see sort of implicitly what the answer to that question is, but maybe I could invite you to kind of say something a little more explicitly, or say it again if I missed it, I apologize, but just, how do you now sort of take those empirical successes against, the sort of drawbacks that you've been talking about?
Good. No, I mean, I think I didn't actually close the loop on that one. So so I think the kind of, so let me be frank, there's a historical picture that I have of really successful theories in physics, that there's a certain type of progress where you have a good understanding of the physical assumptions going into a model. And so that when you discover that there are discrepancies between what you expect and what you observe, that allows you to reflect back on those physical assumptions and either refine the model by adding in further details or change it if one of the principles that you've built the model based upon is really challenged or fundamentally problematic. And so that in the historical cases other historical cases that I've looked at, I think that's been essential, that, doing the detailed work, and this is something that takes centuries typically, is really where the best evidence for the theory comes in, right? So we shouldn't look at the year when a theory is introduced and asked what the evidence is. That's the persuasive evidence that will inspire scientists to work on it, which is important, but it isn't going to give us the best reasons for thinking that theory gives us a permanent understanding of the way the world is or how to manipulate the world and so on. So So the picture I have might just not apply in all cases of physics. So there might be a different way that physics has made progress in other domains. So there's always the risk that I'm taking a set of examples and then thinking that that leads me to a general account of method. But taking on that risk and assuming that this is a kind of understanding of how physics has progressed in other cases that applies here as well, you want more than just a claim that you have a model that fits the data. You want an understanding of exactly what the physical assumptions are that are going into that model that constrain its properties, so that if you discover departures from that, you will then be able to say whether those are compatible with the underlying physics and require a minor modification, or whether that actually undermines the model. And the problem here is that we're taking some of the essential physical features of the scalar field that would be driving inflation and treating that as a free function, right? So if you take inflation just as a phenomenological theory, then you're not really getting any insight into, so you are taking a risk. You're saying these features of the early universe have to be traced to a stage of inflationary expansion, and that has some content. But if you just treat it as a framework that allows you to determine the properties of the inflaton field, and there are no further physical constraints on that inflaton field, there's really sort of nowhere for the process of ongoing inquiry to go. And so the other worry that I'm addressing here is just, do we understand the limitations of the models just as effective field theories well enough to also assess, do we have an understanding of the sort of dynamics of this regime that's relatively insulated from dynamics at higher energy scales, which we know that we don't fully understand. And so there's a kind of preemption threat that if you don't understand that relationship, then the understanding that you've developed of the dynamics in this regime, even though it successfully matches the observations, might be overridden by dynamics at at a higher energy scale. And so part of I've argued this in more detail elsewhere, but the way the field is developed, it's hard to see how the merely phenomenological model building aspect of inflation can really be the start of an ongoing inquiry where you then learn more and more about that regime. Now, there's one response to this, which is just to say, look, that's all you're ever going to learn, right? Like, one response is to, so I think partly historically in the early 80s, people thought they were going to discover the specific field that drove inflation and nail down its properties, and then maybe they could also find it at CERN, right? So there was an initial hope that there would be actually a very definite model of inflation that would support inquiry in the sense I'm describing it. And maybe that's just naive or too optimistic. And maybe all we'll be able to discover is that there's a class of different ideas or different models that would have in common that they produce an inflationary stage. And certainly that's a discovery. The discovery that an inflationary stage is compatible with all the data we have is an important discovery. But maybe that's all that we can discover. So I'm not sure if I quite addressed your question, but you can see then why I'm interested in the question of the EFTs that we're using. How reliable are those? How well do we understand their domains of applicability? Because I see that as essential in thinking of this as the start of a line of inquiry.
Okay, thanks. Yeah, no, that's great. I mean, I nearly asked the question in the form of, could you relate it back to the things that you referenced from George Smith and so on at the beginning? And I take it that's really what your answer is addressing there.
Yeah.
Actually, that's enormously helpful. I really appreciate that. Thank you.
Thanks.
All right, thank you. David Wallace has another question. Please, David.
Thank you. This is actually relating to something quite early in the talk, where you were talking about the kind of workhorse for these inflationary results being QFT and curved spacetime, or else semi-classical gravity, where you're coupling the metric to the expected value of the stress energy tensor. And I'm wondering if that can quite be correct as an account of the physics. I mean, my concern is that what we're seeing here, what we're looking for here, that data is showing, is the structure formation. And structure formation, by its nature, is a coupling to fluctuation. And insofar as the matter distribution is responding to the expected value of the fields, it's just going to sit there because the expected value is basically homogeneous. And I mean, I haven't looked at these calculations a lot, but at least the ones I have looked at in Weinberg's book, for instance, seem to rather explicitly quantize the gravitational field, so that you actually have a coupling of the fluctuations in the quantum field to the metric. And so you've actually got a quantum state of the metric, not just a fully classical metric. I mean, admittedly, again, in the calculations I've seen, you're not quantizing gravitational degrees of freedom. It's all effectively Newtonian, but it still seems to be beyond just the semi-classical regime.
I'm not sure why you think so. So why do you say that the gravitational degrees of freedom are quantized, as opposed to thinking that we're looking at the classical density perturbations once we've somehow made the quantum to classical transition, where the initial fluctuations in the quantum field have now frozen into classical density perturbations. So, and then you do have the metric perturbations at that stage, but it's not clear. So sorry, where is it that you think that we're using quantized gravitational degrees of freedom in this story?
Well, I mean, the quantum measurement problem is somewhat close to the surface here, but
yeah.
I mean, at least if we're still doing unitary quantum mechanics, then things can get as classical as they like, and it's still going to be true that the expected value of the stress energy tensor is spatially homogeneous and can't generate metrical fluctuations. So as long as the thing on the right-hand side in the Einstein field equation,
I see.
Value of stress energy tensor. I mean, that's part of my reason. The other part is just that some of the calculations seem to do it explicitly. But the kind of surely it must be case is based on that point that we can't have the metric coupling to the expected value and as long as we keep evolving the system unitarily, and so as long as we keep the expected value homogeneous and isotropic.
Right. No, I mean, I think you're probably right, and I think I was just being somewhat sloppy in that case. I mean, I think the calculations I'm thinking of, again, there's sort of a range of different assumptions. There are certainly some of them that are just QFT on curved spacetimes, but then when you're doing the perturbation calculation, you are explicitly looking at metric fluctuations. So I think that is probably the case, that you have to be doing, in some sense, a quantum gravity treatment that goes beyond just the fixed spacetime background. So,
I mean, I'm interested in it because it's an example of genuine. It seems to be an example of genuine quantum gravity, i.e., not quantization of the metric, but it's not an example of quantum gravity in the sort of Transplanckian pilot regime.
Right.
And so it's my ulterior motive in asking the question is I'm really interested in how sensitively theories of that form are constrained by the data. And I mean, in some sense, reproducing the spectrum of the fluctuations is a test of a quantum theory of gravity and not just a semi-classical theory.
Right.
I don't have much of a sense of how stringent a test it is. And obviously that's
interesting. Yeah. And
through the inflation, degrees of freedom and fine-tuning issues as well.
Good. No, and I think I agree with you that in some sense, this is all applied quantum gravity, right? Even though it's not usually thought of as quantum gravity proper, that there's, a different part of theorizing that we apply that label to. Whereas in fact, this is already quantum gravity. I think I agree with that. Thanks.
Great, excellent. Thank you very much. I actually have a question as well. So when we look at that or realize that there's very likely going to be a very significant sensitivity for many models on the early state of the universe, you sounded several times as if there's like sort of two attitudes one can take with respect to that. One would be, this is great news, this is a really appealing prospect because we want every window into quantum gravity we can possibly get, and maybe there's something there that we can use and which could constrain our theories in quantum gravity. And I, as a person who works on the foundation of the philosophy of quantum gravity, that's very much something I can relate to. I'm a little bit less clear about the other attitude one can take. So the other attitude sounded like it's a problem, but for whom exactly is it a problem? I'm not entirely sure. It seems as if it might be a problem, of course, for applying effective field theory techniques to inflationary cosmology. And maybe that's just what it was supposed to be. But it doesn't seem to me to be a sort of a bigger problem for inflationary cosmology in general, right?
Mm-hmm.
It's really just a more restricted problem, a point you were making. Or if it's a problem for anybody, then it's for the effective field theory techniques, right?
Yeah, so I think it is. There are, you can find in the literature various people who are advocating a point of view which is very close to what I called indifference, right? Which is, in effect, once we have inflation, we don't have to worry about really anything about the earlier state. You can just make very weak assumptions about what the initial state is going to be like, and inflation will work. And this is often tied to the multiverse picture as well, because then you get people saying, well, as long as inflation produces a multiverse, then, the variation in conditions in different bubbles in the multiverse will be so great that you don't actually really have to worry about the initial state at all. So it's partly a response to that line of argument that it does seem that inflation is more sensitive to higher energy scale physics than and it isn't a problem in itself to be sensitive to higher energy scale physics. I mean, the standard model has both the Higgs mechanism, the hierarchy associated with the Higgs mass, and the cosmological constant problem. So it's not as if that means that we should throw away the theory, but inflation does seem to be more sensitive to UV scale physics than other cases where we've used effective field theory techniques. And sorry, my dog is barking in the background. I hope that's not distracting. But it's more for a particular approach to inflation. I think this undercuts that position. As I said, as I meant to say at the end, it's not really a problem for inflation in the sense that I think we can just shift to thinking of inflation as another possible dynamical phase in the early universe, which isn't replacing a theory of the initial state or of a theory of origins, but it's just a phase that there's some earlier state that had to have certain properties for this phase to take place. And this is, sometimes people talk about like the dominant channel, like it's a way to get from a wide range of initial states to something more like what we see. That doesn't mean that you entirely get rid of the theory of origins. It's just now what you need as an initial state is changed because of the intervening inflationary phase.
All right. Okay. That's actually very helpful. You're quite right. I forgot about this attitude or view of indifference. That is, of course, affected as well. Yes. Okay. Great. Thank you very much. Mike has another question. Let me promote you. So please go ahead, Mike.
Hi again.
Hi.
I wanted to mash together a few of the questions that have come up, or really your responses to them, just to get a fuller picture. And in particular, this is the sort of post George Smith line of the details that make a difference. Up against, you brought up Ricard David's framework and so on. And I guess the question that these two responses brought to the surface is, when I think of the Newtonian case, I think, okay, we're after a force law, and the thing that is being committed to is the square. And then having committed to it being an inverse square law, you can deal with the details that make a difference. And this is very important. But then when you were talking about the David adjacent aspect of this, is that the different proposals for early universe scenarios were reconstruing what is the total evidence set in some sense, or sorry, I shouldn't have said the word evidence because that's dangerous in that context, but what is the content that a theory of early universe is supposed to be beholden to? And I'm wondering, is there an interesting tension here, or is this just a slight generalization of what the spirit of George's program applied to this context? Yeah, so if you could say more on these points.
Yeah, I think this is where so I don't really like Lakatos's approach, but there's, I think, a useful way of thinking that you have research traditions in some sense, which one of the things that I think is hard to have, I mean, one of the things that characterizes a research tradition is an understanding of the domain of phenomena for which a theory should be responsible, right? So an understanding, for example, that this is the domain of phenomena that gravitational theory should be giving us an account of. Obviously, from Aristotle to Newton, there's a huge transition. And similarly, I think we can have more fine-grained transitions where you ask, what are the sort of phenomena that you're going to take as the most reliable measurements to use? And so there's sometimes these more fine-grained assessments like, well, we don't trust what the people are telling us about galaxies. We trust the CMB. So for example, in cosmology, you see that there's a huge amount of confidence in using the CMB because the physics seems relatively very well understood. It's really just linearized perturbation theory. And so I think when you look at a debate like Mond and dark matter, part of that debate is what domain of phenomena is the theory really responsible to? And so what I'm suggesting is that in some of these alternative accounts of the early universe, I think there's something like that going on, that there's a question of what is it that is really the aim or the domain of phenomena that you need to address. So, but going back to George's, so how does this relate to George? I do think there's kind of an initial assessment of, what's the domain of phenomena that Newton is going to describe using the inverse square law. And obviously he was open to the possibility that there might be other forces that would be relevant. And so the restriction to the gravitational force, I think, comes in more as one of these idealizing assumptions that at some point you might have to, maybe in dealing with tides at a certain level of complexity, you'd have to allow for non-gravitational forces at some point. So I think the framework assumption is partly constraining what you're allowed to introduce into the models, but I don't think it's limited to just the gravitational force. Sorry, that was, I think, going off somewhat on a tangent, but I think you're right that there's a kind of bigger question about how to think about what the domain of phenomena the theory should treat. And I really think you have to shift into a kind of higher level assessment in terms of research traditions or something like that to acknowledge those kinds of changes.
Great. Thank you. Yeah.
Thank you very much. Daniele Oriti has the last question. Please, Daniele.
What a honor.
Good to see you, Daniele.
Hi, Chris. So there are a couple of comments, actually. One refers to Chris' question. For what I understand of the opposite camp, meaning those that are not pleased by a dependence of inflation on quantum gravity issues, I think that the problem is that, okay, on the one hand, it's practical because we do not have a unique theory or a consensual theory of quantum gravity. It's like, saying that in order to solve problems about inflation and cosmology, we have to load ourselves of a bunch of other problems that are at least equally difficult and unsettled, and that's in itself not pleasant. But in general, the degree of how much each one of us has to be pleased or not pleased about this dependence on quantum gravity has to do with the degree of universality of what quantum gravity has to say about the early universe. Because even for a quantum gravity theorist, it would be terrible if we had to say something about inflation, but the answer we give about questions in early universe cosmology depend on the fine details of of a specific model, or on a bunch of other assumptions, or if other quantum gravity model comes with 200 new parameters. With no degree of universality in the predictions. And the second comment is related to this because somebody raised the analogy with, well, the connection with the analog gravity models. And in that context, you see exactly this type of issue. So a lot of people are pleased that we get sort of quantum field theory on curved space-time in some analog gravity system. But the reason why they're pleased is that this is a quite general way of describing the effective theory of phonons or quasi-particles in a fluid. If it was not the case, and the statement was that for some specific condensed matter system in some particular regime, for certain values of parameters, you could get something that looks like nice quantum field theory on a curved background, it will be terrible. Either it will be not useful, or it will actually just make everything more complicated. So I think that's one way to understand also the dependence between inflation and quantum gravity, for what I understand from your talk and other stuff.
Thanks. That's very interesting. I mean, I think this suggests that so I mentioned that there's sort of one camp that in the early days of inflation thought that they're going to find a specific model, it's going to be an SU5 Higgs field that drives inflation. I think there is a camp that now just says there's just a whole class of different scalar fields that would all lead to inflation. And maybe it's this sort of the line of thought you were suggesting. It's kind of like universal behavior, that if you have scalar fields with a wide variety of properties, could we say that they'll all lead to an inflationary state, right? So it's sort of, rather than thinking that you're going to discover the details of the specific scalar fields driving inflation, if you just make a much more generic claim, these sorts of fields seem to be allowed by physics at that energy scale insofar as we understand it. Here's the very weak constraints on what kinds of properties they'd have to have. And so then we just expect inflation to occur. So I think that is, for some inflationary cosmologists, I think that's part of their reasoning, that it just seems like, yeah, they're not as interested in the further question of which field is it, or which, it's more, is there a plausible model, and perhaps there's a whole lot of them. And partly then my question about whether this is the start of a new line of inquiry might seem naive. It might seem the line of inquiry you want to pursue is exactly the thing that you were saying condensed matter theorists want to avoid, right? Yeah.
In a sense, what I'm saying is that either the same thing happens concerning this dependence on quantum gravity, that we find that there are some very general features that characterize this dependence and do not really, refer to specific details of quantum gravity scenarios. Or we be basically like 20 years ago back in the story of inflation, in which we had to hope that there is some unique theory of quantum gravity, and until we get it, then we cannot say anything about cosmology.
Yeah, thank you.
Excellent, thank you very much. Please join me in thanking Chris once again. We should end this seminar by announcing next week's seminar. Next week, Faye Dowker from the Imperial College in London will be our seminar speaker, so we hope that many of you will join us again. Thank you very much, and bye-bye. Goodbye.
Thanks, everyone.
Yeah, thanks very much, Chris.
Do you want me to stay on at all, or?
Well, why not for a minute or so?
Okay.
I stopped the recording, okay?
Yeah.
Okay. I'm very sorry.